Good evening to you all. My name is Annie Richardson, and I am an outreach specialist in the Earth Science Public Engagement Office. Now, friends, our home planet is dominated by water, and in its many forms, the cycling of water and energy through the atmosphere and ocean is crucial to life on Earth. Yet the ties among the water cycle, ocean circulation, and climate are poorly understood. One of the keys to understanding this cycle is sea surface salinity, and that has never been measured from space. Aquarius, a joint mission between NASA and the Space Agency of Argentina, will measure sea surface salinity to monitor variations in the water cycle, from land runoff, sea ice freezing and melting, to evaporation and precipitation over the ocean. Global sea surface salinity data will allow us to create unprecedented computer models that bridge ocean, atmosphere, land, ice systems with the goal of predicting future climate conditions. Now, one of tonight's guests is the JPL project manager for the Aquarius mission. He has been the Aquarius project manager since the inception of the project, and for the last 9 years has been working with the Argentine Space Agency towards the development and testing of the Aquarius SAC-D observatory, which is currently underway in Bariloche, Argentina. He started his career at NASA in 1985 and has held positions within NASA on various projects and missions such as the Hubble Space Telescope, the new technology-based Deep Space One, various new generation ground and space-based astronomical cameras, Earth observing missions, space shuttle experiments, and ground data systems for spaceborne missions. Prior to joining JPL in 1991, he worked in Maryland at the Space Telescope Science Institute in Baltimore and at Goddard Space Flight Center in Greenbelt. Before his appointment as Aquarius project manager, he worked on the Galaxy Evolution Explorer, an ultraviolet astrophysics mission investigating the birth of galaxies and star formation. Now, Mr. Amit Sen thoroughly enjoys the challenge of working on space-based projects, new technology, and international missions, and has worked with the space agencies of Argentina, Brazil, Canada, France, Italy, Japan, and the European Space Agency. I guess he could be his own United Nations with all of that experience. Now, away from work, Amit also enjoys movies, traveling, especially to warm beaches, and cooking tasty exotic foods. Included among his numerous NASA and JPL Achievement Awards is the NASA Exceptional Achievement Medal. Now, friends, so that you can get the full flavor of this very exciting mission, joining Amit Sen tonight is the Aquarius project scientist, Dr. E. Chow. E started his career at JPL in 1983 with a PhD in oceanography from Princeton University and postdoctoral training at UCLA. He is now a principal scientist in the Climate, Ocean, and Solid Earth Science section. His accomplishments include extensive publications in the areas of oceanography, atmospheric and oceanic sciences, and climate change. E has garnered many awards for his work, including the NASA Exceptional Achievement Medal. His hobbies include hiking, traveling, and a daily swim at the Rose Bowl Aquatic Center. Ladies and gentlemen, Please join me in welcoming tonight's guests, Aquarius Mission Project Manager, Mr. Amit Sen, and Project Scientist, Dr. Yi Chow.
Thank you. JPL, the way it is, and the recent planetary events that has surely come about in mind are, if you look around the world, around the room, is about Mars and is about planetary missions. So NASA and JPL, the things that surely come into mind are things, somebody's watching us, and somebody's watching us from far, and the planet that we want to be in, and we want to explore what happened to the planet where the water has disappeared. So in the search of water, our rovers are still humming around and talking to us every day. So that's Mars. So let's now change our focus to somewhere a lot closer to us, where we live. Some place where it's twice as big, a lot more cozier to be in. And I can tell you one thing, that this is a very unique place in this world, and you guys all know about it, but it's always good to hear that we are so fortunate to live in a place where we have only found the abundance of water, right, an abundance of life. And that is something that we are going to go and look at. Once again, the operative word is water. So, being at JPL, the emphasis on space exploration falls into many areas. And primarily, if you look at the area of Mars, there is a whole section of JPL, a quarter of JPL, works on projects on Mars. It's pretty big, and we are the pioneers in moving that. The next comes the planetary. We have sent probes from so many years to different planets, even outside the solar system. So that planetary missions are another quarter of JPL. The third quarter is an astrophysics section where it looks at the heavens, looks at stars. Just like Annie said, my previous mission was looking at the birth and evolution of galaxies and stars. And pictures in the back would also show you the images that we have found from places. And so the astrophysics mission, and of course Hubble Space Telescope is one of them, who gets you the most beautiful pictures that you've seen in the heavens. By the way, folks, I will digress your thoughts for 15 seconds, even though this is an Earth talk. Any moment that you can get, look behind you. That is the Wide Field Planetary Camera, right, that has been taken back from the Hubble Space Telescope and has come back to Earth. That has taken one of the most wonderful images in this whole universe that we have seen. So take a moment later on after the talk to come and look at it. I did work on it, so it's a very close to something that's in my heart. So that's been to space, and now it's back. And now, saying all that about astrophysics and everything, we need to talk about Earth and the Earth that we live in. So with that, what I was going to suggest is we look at Earth and some of the crazy facts that we always look at. We read the books, we look at the newspaper, we look at the internet. It's buzzing with Earth facts. And often I look at a map and I look at the world. Every time I look at it, I find something different, find something fascinating, and I hope you do too. And one of the main things I wanted to point out is the Earth is old, and it's been there for a while, for about 4.6 billion years. It's a little bit younger than the sun, and with a high population, about 6.8 to 7 billion people as of this May counted, and a growth of 1.3%. So in about 60 some odd years, we'll double our capacity of this Earth. So just imagine what it's growing at. And working with different countries, I just wanted to let you know there are about 195, 196 countries around the world. But the vast majority that I want to point your attention is the water versus land ratio. 71% is water, and we live on that 29%, which we call land. Now, looking at the same picture, but in a black and white way, because I want to emphasize the ocean. The ocean is vast, and it's about the size that I said, about 71%. So about 140 million square miles covers the surface. And about 97% of our planet's water are contained in the ocean. So just imagine that water bottle or fresh water that you're drinking, is about very little amount that we can carry other than what's contained in the ocean. Now, the top 10 feet of the ocean holds as much as heat as our entire atmosphere. It's quite important to us to know that because the atmosphere touches at every moment, right, on the top of the water. So that has the heat change, and of course, our wonderful friend over here, E, will let you know a little bit more about oceans because he is an oceanographer. His whole life has been dedicated to looking at ocean and understanding them. So the next 2 pages are wonderful pictures that fascinates us. Of course, this is the warm beaches that Annie was talking about. And it's not that I would love to be there. It's always fun to talk to people who are interested in the missions that we do. I'm not going to go through each of the line items that are listed on the facts of ocean, but I just wanted to let you know that this Earth contains so much living creatures, and yet 99% of the Earth's living space, right, is we have the oceans that carry them, and 10% of the living space is occupied by humans. And moving on to certain things, that there are features on this Earth that can be viewed as far away from the moon, the ocean features. And just imagine, the moon is about 250,000 miles away from Earth. So moving on to some other exotic pictures and wonderful visions, we see ourselves that even though the water is there, it's kind of cold. It's about 2 degrees Celsius, right, or about 39 degrees Fahrenheit. And if that temperature hits Los Angeles, you know what happens. Everything kind of falls sleepy, and we get the warm coats and everything. And 3/4 of the world's mega cities are by the sea, such as Los Angeles, close by. 80% of the people love to stay near the beach, right? And more than 90% of the trade that happens between countries happens between sea lines and the ships that carry things back and forth, and even what you see every day, the use of the internet, the use of the telephones, right? There are submarine cables that connects between continents, and that carries your traffic more than you think that it's going up to the satellite and coming down, right? Those trunk lines are essential for communication. So that's a snapshot on letting you know how important Earth, oceans, and where the planet we live. So at this point, what I'm going to do is, how about you excite us with some science, right? And
Yeah.
rather
Let's
than
go
having
for it.
Earth facts.
Yes.
Okay?
Yes.
Let's go.
Let's move on. There are so many areas NASA Earth system science has been studying in the past many decades. We have been trying to organize them into 6 different thematic areas. You are familiar with the weather, which is showing in the lower left panel, and the Earth's surface interiors, dealing with the seismology, the earthquake, and then in the solid Earth aspect, and the climate change on everybody's mind these days, the carbon cycle, our ecosystem, the atmospheric composition, including the air quality, and how do we control the atmospheric different species, and also the water cycle and the energy cycle. So those are among the 6 different thematic areas. The mission Aquarius we're going to talk about today touch on 2 of these 6 thematic areas. The first one is climate change, which we will go into a little more details next, and also the water cycle, because ocean salinity is part of the tracers, and then tracing all the way the fresh water from the ocean to the atmosphere to land and then back to the ocean. So moving on to the climate, the first thematic areas of the climate change, like the weather, they changing every day. It's from the summer to the winter, from the year to year. So this movie give you one example how this ice sheet in the Arctic is changing from 2 different years, from 2005 and 2007, and then see how much ice being melted within a few years time frame. And then if you put California into it, you can see how much the big area is covered. And then imagine the fresh water pumping into the Arctic Ocean and then going to the entire ocean system and then changing our Earth.
That's a drastic change.
Yeah, it's
in 2 years.
Imagine the size of the California.
And that doesn't even, that leaves areas around that are not covered.
So imagine this is one of the many phenomena. Climate is changing. They're changing constantly, keep in mind. And you work with engineers on it, and think about this particular phenomena. How do you measure them in the effective manner? It must be very challenging from an engineering perspective.
It is. Well, let's go on and see how we look at things from space and things that we look from close and look from far. Wonder that's going on over here. There are two pieces of information, and if I look very close, I really don't have any clue what I'm looking at, something puzzling to me. And what we are trying to state is when you look something very close to a scene, what we call a local view, you normally don't get the picture. Everybody says, see the big picture. And this is the concept that I thought would be very important to show, that when you look very close to your local area, local environment, local area that you're living in, things might change, and you think that's happening globally. That may or may not. And what it means to us, when you step back and look at, you get a global view of things. And what you just saw from those two snippets are the picture of the Mona Lisa and looking at Earth in one of those small areas. So you need to step back and look at how to look at Earth in different ways as a total. Now, NASA took up this challenge and said, well, we're going to observe the Earth and ocean from space. What we will do is we call remote sensing. Now, remote sensing is not something new. It's happened about in the 1800s, right, when people started putting together cameras. So these cameras that they put together, and the pigeon is a really nice one. During World War I, these are Bavarian pigeons who used to have a camera attached to them. They would fly over to take pictures of castles, right? So that was sensing something remotely. Now, as I was going to explain remote sensing, it's most aptly put by one of the website articles that I have from Goddard Space Flight Center. It says the term remote sensing, first used in the United States in the 1950s by Mrs. Evelyn Pruitt of the U.S. Office of Naval Research, is now commonly used to describe science and art of identifying, observing, and measuring an object without coming into direct contact with it. The process involves the detection and measurement of radiation of different wavelengths reflected or emitted from a distant object or material, by which they may be identified and categorized and classified into substance and spatial distribution. All this means is you are looking at things from far away and trying to figure out what it means to us. And you will see in our presentation as we go about. Now, I do not want to go through each of the pictures, but as you know, that was Explorer 1, and Dr. Pickering and von Braun and Van Allen are holding up Explorer 1 that started the space race. And so you have seen probably the picture when you're coming in to von Kármán today. So I just thought the relevance and reference to it is more apt. The picture that you saw of a satellite over there is called Landsat. And that changed how we looked at Earth, right? Launched in the first Landsat was launched in 1972. They've been giving us, and there are many generations of Landsats that's going on, taking vivid pictures of the Earth in different ways, different modes that we can understand today. So now, understanding pictures is one thing. Also trying to figure out what are the things that the satellite network is monitoring or important information that's providing or it's missing. Now, over the last 20 years or 25 years, NASA has sent a lot of satellites that are orbiting around the Earth. Currently, they're enlarged in the numbers of thousands that are either space junks or operating satellites. But of all them, satellites have their own life and their mission life. We have put satellites up in space to monitor rain, the TRMM program, the winds over water, the scatterometer program like QuickScat and Sea Winds. And we have measured ocean color, like sea whips, find out vegetation and algae in water. We've measured sea level, which is a sea level rising or falling in certain places, with the JASON and the TOPIX missions, and the OSTM, the new ones. We have measured surface temperature in many satellites, Well, one thing we have never measured from space is surface salinity. And why surface salinity is important, E is going to tell you all about it, right, E?
Yeah, sure.
And so we just wanted to make sure that you understand where Aquarius fits into this puzzle. So the Aquarius mission, which we will make you go through with us, is about understanding the interaction between the global water cycle, which he's going to demonstrate and look at it with videos, ocean circulation, which he's going to show how this wonderful conveyor belt system is in place in our wonderful world, and the climate and the measurement of sea surface salinity. So now with that, how about you take us to S&S?
S&S.
Salt and salinity.
All right. So now you start to wonder, you may understand how to measure temperature from space. And how do you measure salinity? How do you tell how salty the seawater from space? That sounds pretty difficult concept. I never realized before I come to JPL you can do that. So
You don't have a thread going down from the satellite and touching the water.
how long that can be?
I don't know.
How many miles?
It's going to be complicated.
That's pretty long, right? So let's take one step back and let's start with the salt. So you're familiar with the salt concepts and then using to preserve food and used in the industry. Primarily sodium chloride content. Those are the salt crystals showing on the right. You can find out in Wikipedia and any website you can find. But we are not less familiar with the salinity, which is defined as a measure of the salt content in the seawater. So we define the salinity as a ratio between the salt content in grams per kilogram of seawater.
More like parts per thousand.
Exactly. Right? So there's no unit to it, but you can think about in typical ocean, we talk about 30 to 40 gram per kilogram. So we talk salinity unit in typically. So that's give you a concept of the salinity, and then here is a picture of all the historical data collected in the last 150 years and digitized into a chart, and then show you how complex the salinity is changing from place to place. In those places in the blue areas you see in the lower 30s, primarily they're near the ice, near the rivers, or where you have a lot of rainfall. Where you have the red areas is very salty. You tend to have a lot of evaporation. If you ever be Mediterranean or some middle of the Atlantic and the subtropics and have very salty water, you can keep the messages from lower 30s to higher 30s. And Aquarius is going to make these maps move in time. So every week we're going to take a snapshot of the ocean, give you a map of the salinity, and you're going to see how they change from week to week, from season to season, from year to year, and hopefully from decade to decade. And then and turned out Aquarius can measure the salinity very accurately. After working 10 years on this mission, it's still amazing to imagine they can measure the salinity up to 0.2 part per thousand. So just give you an idea, 0.2 part per thousand, we call it practical salinity unit, just to simplify it. How do you measure this accurately?
A pinch of salt is about 1/8 of a teaspoon.
1/8 of a teaspoon in 1 gallon of water.
So just sprinkling something over, say, French fries or something like that,
Right.
that we would do.
And you are not allowed to touch the water.
And you are detecting it 657 kilometers, roughly about
From space.
408 miles above the
Exactly.
Earth. About the distance from Los Angeles, a little beyond San Francisco.
Right.
So it's amazing that you could measure it with that precision from that far away. And that is what makes Aquarius so unique, that our instrumentation is so precise to measure something like this. Now, this is all so good. What does it mean to us?
Let's keep going. So Aquarius measures salinity. What it can tell you, is give you really, as I said, is give you the maps. We are able to take decades to accumulate, and then think about collecting water samples and then measure how salty they are, how quickly you move your ships, and then from place to place. And then Aquarius give you a weekly map of salinity, and then give you really a new perspective on how ocean is changing, how it regulates climate. We live near the ocean. We know how the ocean modulate the weather. They're going to do the same way, modulate the climate. Showing here is a so-called global conveyor belt. it's a kind of the simplest way to conceptualize how the ocean moves. And the salinity and the temperature determine the weight of the seawater, and that's drive the overturning of the ocean circulation. And this is the simplest way ocean is moving. The North Atlantic is going to, you see these Gulf Stream areas coming here, and they're going to sink to the bottom and then go to the circle. And then we were put in the movie next and put this into motion to appreciate how this conveyor belt is circulating around the globe. So the water, when water became heavier, they're going to sink to the bottom, right? So they move from the Gulf Stream area to the North Atlantic, and they're getting cold because of the cold air mass from the lands, and they become heavier than the surrounding water in the northern North Atlantic. And then they start to sinking motion, mostly to thousands of meters. So you see this vector moving arrows, and then they diving down to thousands of meters, and then returning back to the south, and then being part of this conveyor belt. And how quick, how fast, and how slow this conveyor belt is moving, and play a big role of the climate system and our European continent, so the weather system in there.
Is this why England doesn't freeze?
That's
because
right.
It's way up.
They are very high latitude, but they're not as cold as Canada. Salinity is a key tracer to trace the whole water cycle. If you have a rainfall, you have the ice melting, you have a river, fresh water dumping into the ocean, you increase the mass of the seawater with the same salt, and you're going to decrease this ocean salinity, right? And then the same thing, you're going to freeze out in the seawater in the certain areas, and then you're going to increase the salinity. So the salinity is a key tracer to trace the whole water cycle, how the fresh water evaporates from the ocean, moving to the continent, and then become a rainfall, and then eventually come to the rivers and the runoff, come back to the ocean. So imagine, without knowing the salinity, it's almost like a missing piece of the puzzle.
Okay.
Does that make sense?
If this is the effect, do you have a video that you can show us that makes us understand the connection?
Let's keep it moving. These moving clips where it get you a little bit dizzy if you're not familiar with, if you ever take a small boat in the middle of the ocean, and this is probably what you'll feel. It's a lot of changes, a big percent involve atmospheric precipitation and ocean evaporation. A lot of circulation waves moving around. It's a complex system interacting between the two systems. The evaporation, precipitation were changing the salinity, and they were changing the density. So the water mass is changing, and then once the water is heavier, they join this conveyor belt again. So the salinity is a way to drive the ocean circulation. That's why we want to launch the satellite to measure these key variables, so we can identify where the water sinks, where the water come back, and how they circulate, and then modulate the climate. And it's not only the North Atlantic, it's everywhere in the globe, because this conveyor belt will touch on every part of the globe. For the schematic region, if you can look at the real 3D picture, there are going to be many, many moving elevators and then conveyor belt into the area. It's not only affect the fresh water, also transport heat from equator to the pole. So how slowly, if you slow down or you speed up this conveyor belt, you're going to dramatically changing the weather and then the climate you live in, the way you enjoy the warm beach or change.
And there are movies like that Hollywood has put together that some of you guys have seen. But is that something so quick it happens?
You just fast forward many, many, many zeros, and then you're going to see that movie, basically. So affect our lives, and then salinity not only abstract, is not an abstract variable, because it will come back to us, is a key variable to measure and then eventually help us to predict.
Okay. Well,
all right. So historically, the salinity measurement is very challenging. You have to go to the sea, taking the water samples, measure salinity. This chart on the right is to illustrate is 100 years if you plot the location of the change of the salinity. And you can see from time to time, a few years, no ships cross that particular location. And that's give you an idea how difficult to measure this. And that's the Aquarius space perspective give you an unprecedented measurement because give you a weekly map of salinity changes.
So what you're showing is ships of opportunity that has taken samples of water, or buoys that are installed in the ocean has taken samples, and this is the sparse data.
Plus the researchers and from time to time go out to measure ocean water. So this unique measurements provide really unprecedented data coverage to help us to understand how Earth's changing, and then eventually will help us how to predict the future climate change. So giving those importance, it's not easy to come up with a mission like this, and you need to read many of these books of the smart people to come up with a way to measure salinity. This is what we call the salinity chart. You can measure the brightness temperature of the seawater, and by knowing how warm the cold temperature, you can read the value of the salinity. That's how they measure, we call the brightness temperature. And so we take many years to develop, take actually 2 decades to work on this theory by the community. Hundreds of thousands of scientists worked through the many decades. And then about 10 years ago, GAPL designed a lab experiment, tried to demonstrate we can reproduce this theory with our instrument. So we mounted a radiometer at the swimming pool we built up in the mesa on the hill in GAPL, and then look right there next to you. This is exactly like you taking temperatures when you go to a doctor's office, take your air remote sensing. So you take this radiometer, measure the salinity. We have a truckload of salt here. We can put a different salinities and then see whether we can reproduce this. So there's lines and the symbols, and then we are reproduce theory almost exactly. So we are very happy about this lab experiment. And it takes to the next level. We put in a big airplane, the C-130, the huge airplane. You see the 6-foot colleagues here. You mount this one and then fly the airplane with door open because you have to look at the ocean. This is too big to be mounted underneath. I was on the boat, by the way. I'm afraid on the plane. So that now you go to the ocean. Ocean is very rough. You need another instrument called a scanometer, measure the roughness and help you to retrieve the salinity. And then you validate from the boats. And I was there for 2 days and collecting water samples. This is a PVC pipe from Home Depot. And then you're going to pipe to the boats, and then you're going to run into measure salinity. And we compare what we collected on the water, what we measured on the airplane, 10,000 feet. And then we are convinced we can do this from space. And then if we go to hundreds of miles. So after this, we are convinced Aquarius is feasible, and Aquarius is born at that point.
That is true, E. And E and other scientists have put together this technique, and we are now extending the technique from the airborne system, first of all from the laboratory, to the airborne system, and now to space. As was pointed out, this is NASA's first measurement to measure sea surface salinity from space. The European Space Agency had just launched a mission that can measure salinity, but at a different precision and in a different way. So, but this is NASA's fold. Now, with the birth of Aquarius, and as you guys know, Aquarius is a sign in the horoscope, very catchy name, and it has to do with water, right? And it's also a constellation that is one of the faintest constellations that you can see in the sky. But it always amazes me when I see an object that symbolizes things that we are doing. The ribbon that you see in the middle, this is our logo, by the way, and you will find a few of those stickers lying when you're going outside. Please do feel free to take some for yourself and for your friends to pass the information around. So the ribbon that you see is the global conveyor belt that E just demonstrated and talked about. And of course, Aquarius being the water bearer, as you guys know in Greek mythology, Zeus picked up Aquarius to become the water bearer, to bring them wine or bring them some fruit of nectar or the water itself. Now, from the olden times, some of the Egyptians and the Greeks, they just loved Aquarius because in the drought season they brought rain, whereas the Babylonians hated him. They said, well, when it rains, it causes flood and it causes devastation. So there is good myths and bad myth about Aquarius, but no matter what, it has to do with water, and we want to symbolize and understand that it's a concept that has been there from ages. So moving down, I'm going to try to explain to you in short ways how the mission is and how it goes about. Now, don't get scared about the complicated diagram, but what I wanted to say is when we launch Aquarius, Aquarius is going to be above the Earth at 657 kilometers above and going around the Earth every day at 15 times a day. That's a 90-minute orbit. It's a sun-synchronous exact repeat orbit. That means it comes back to the same point in time after 7 days. So if Aquarius images one portion of the ocean, that same portion of the ocean, it goes around, the Earth turns around, it'll come back to the same point. By that way, after 7 days, you will be repeating the same area, and over multiple repeats, you can get a trend. You can get a better estimate on your errors that you're collecting. So that's why the global coverage is in 7 days, and it repeats 4 times a month, of course, in the same area. So as he pointed out, there are 2 instruments that are on board, the radiometer and a scatterometer. And they point towards the night side so that the sun, when it heats up the water, does not contaminate the temperature and the measurement. The only other thing that I was going to point out to you, the width of the beam that is crossing over the ocean is about 400 kilometers wide. It's got 3 beams, and I will point out to you as we see pictures of the hardware being made. Now, in a summary, I would say the mission goes like this. From the start of it, we are now putting together Aquarius and testing it, and I will show you some pictures of that. Now, once we are ready, in April of 2011, we'll be launching it from Vandenberg Air Force Base. And after it's launched and goes into orbit, it deploys itself, and we monitor and collect information. That information is downloaded through a ground station. And these ground stations are all around the world. The one that you see over there is in Argentina. That information is put together, downloaded, processed to make an image. Remember, when satellites take information, they're all bits, right? You need to construct maps, construct information that is useful for us. So once we collect the information, we validate it. How good is that information? Or is it just information we collected? That's the validation part. And then we give it to the community. Remember, Aquarius data and other data from NASA is free for everybody. Anybody can use after it's validated. So that's what it goes back to the community. Now, this is the mission that we're going to talk about, right? It's in glory. It's an artist's rendition looking at Aquarius from space. But I just want to point out that I just will walk up to this area. This part is Aquarius, and the rest of it is the satellite that hosts Aquarius. The reason why I wanted to show you this is because the portion that you see, the Earth, is a real image from another spacecraft. Aquarius is not there, and we cannot ever take a picture like this. So this is the east coast of Argentina. And why am I pointing it out to you is because just a few months ago, Aquarius was sitting right at that spot, if I can point out with this laser pointer. This is Bariloche, Argentina, right, where all the instrument was put together and tested. So just wanted to show you that it's almost like it's looking back to its place of inception. Then let's look at partners. We cannot do things by ourselves, and that's why I have E over here to help me out all the time. So, talking about the partnership, this is a logo also developed by the Argentine Space Agency. And their Argentine Space Agency is called CONAI, much like what we call ourselves NASA. And you see the representative flags down there. The other agencies that are part of this mission are the Italians, the French, the Canadians, and the Brazilians. They all contribute portions of this mission in some way, fit form. Now, one thing you might ask at this point, what is SAC-D? What kind of a name is this? It is a name that it's also in Spanish, but it roughly translates to, it's an application satellite, item D. So that means there has been A, B, C, and now it's D. And all the 3 earlier missions, Argentina has done it with NASA. So this is NASA, and Argentina has been doing this for the last 15 years together. The last one, SAC-C, was up in space in the year 2000 and is still operating. Now, when we look at our partners, we talk to them every day, different social customs, different languages, different ways of life. And yes, we live in North America, and we're not used to this kind of a picture, but when we go to South America, they love this picture. They think that's the right side up, right? And all I've done is shown you pictures of where things are. The dots that you see in South America over here are where Aquarius was in Bariloche. This is Cordoba, the ground station that I showed you. This is Buenos Aires, right, the headquarters of CONAI. And this is currently where Aquarius and the observatory is sitting. It's in Brazil. And so I will show you at some point how the journey of Aquarius had taken place. But let's talk about the technology a little bit. This equipment that we have created is pretty large. And as you see, this is the 6-foot person that is standing over here. And if you have it in its own glory, standing inside the rocket fairing, that is about 16 feet. So that's quite tall. So it is almost touching the top of the ceiling over here. So that's how big it is. And if we were to unfurl the arrays, it would probably cover from the whole podium, from the podium over here, all the way to the back. So it's a rather large machine. And not only it's such a large machine, it weighs about 1.5 tons, right? So we have to get this equipment up into space through the rocket that we are going to go on. So these are the experiments that are contributed by different agencies other than NASA and the Argentines, and that's how it is shown. Now, what I showed you was a cartoon, and today when we have built things together, this is how they look like. And so once it's been put together, we call it a piece of beauty, because this is what we have all worked for, and me for the last 9 years. Now, let me take you to the journey where Aquarius has been. Now, most people are familiar with when they get on airplanes, they whip out their cards and say, I want frequent flyer miles. And this is how Aquarius earned its frequent flyer miles. It all started off at Goddard Space Flight Center in Maryland. It's right over here. And this is, once again, what I want to point out and make you remember, called remote sensing. Without remote sensing, from far, we know. This is a Google map, right? And from Google map, you can see Greenbelt, Maryland over here, and the Potomac River over here. So Aquarius makes its journey from the construction of the radiometer at Goddard, and then comes all the way by air transport to JPL, sitting here in Pasadena. As you will see from time onwards, all the hardware that was put together before it was shipped out is shown. So once again, you're sitting over here, that's JPL. And then let's take a step through time and see what happened when we shipped Aquarius to Argentina. Needless to say, the movie contains the making of Aquarius from the time it went to Argentina, and there's an audio cue. You will see the president of Argentina, even part of the movie. I cannot find a better place to work. See here, we have a beautiful view of the Earth down below of the satellite where it parts.
Este es un momento histórico para la empresa.
Este SAC-D está en las etapas finales de fabricación.
Argentinos construyendo junto a la NASA un satélite
This is before we went to Brazil. This is a building a few blocks away.
La ciencia y la tecnología en la Argentina han tomado el lugar que le corresponde.
Se va a montar sobre un satélite construido íntegramente en Argentina y por científicos argentinos.
Se trabaja mucho cuando uno viene a Bariloche, pero también se disfruta porque se consiguen cosas, los logros que se obtienen son muy reconfortantes.
Científico que hace que ambos países trabajen con un objetivo común. Así que, al igual que los satélites anteriores, el A, B y el C, este es un proyecto que tiene mucho interés para ambos lados y tiene mucho periodo de inversión.
Over the last 10 years, I've been working with our Argentine partners, and they're incredibly talented and individuals, very personal, dedicated, and their willingness to work together and help. That has been the most key element that I can say. It's not only the Argentines that I am talking about. I'm talking about the Italians, the French, the Brazilians, the Canadians. All these individuals are extremely talented and are willing to work together. That is something that you don't always see in other programs or missions. So I'm very, very fortunate to be part of that team.
Every day create your history. Every night music, your leaving your legacy.
Los datos que van a ser provistos por el instrumento Aquarius son únicos, van a ser accesibles también aquí en el país y plantean el trabajo para la comunidad científica a nivel global.
Una misión que es la más importante que hemos empleado hasta ahora. Es una misión con la NASA, donde CONAA y NASA, la Agencia Espacial de los Estados Unidos, han trabajado conjunto como socios.
So our work here is to finish the integration of the Kármán 1 experiment. Kármán 1 is in fact an experiment dedicated to the measurement of space radiation, its effect on electronic components, and also the measurement of space debris and micrometeoroids fluxes in space.
Entre julio y aproximadamente diciembre de este año vamos a estar terminando para que antes de fines de enero del año que viene nos vayamos desde Brasil a Vandenberg para tener un exitoso lanzamiento del Sagre y Aquarius el 1 de abril del año que viene.
I'll tell you, this is always an exciting day when we work over there. We haven't built a satellite like this before, and every satellite that we build are unique. So we face challenges every day. We get amazed how things work every day, and how good our engineers and our scientists are. And so this is just a pleasure to work with. So we will go forward with the rest of our presentation. And as I took you down to the journey, and the journey took us all the way from Goddard to JPL all the way to Bariloche, where you saw the U.S. Air Force plane land, the military airplane. And then they took us down there, and the next section was what we did last June. We took airplanes back again and put it to Brazil. This is where it stands in Brazil. This place where we are testing right now is midway, it's more closer to Sao Paulo than Rio, but it's midway between those two big cities. We are going to do our environmental test campaign. What it means is, for those of you guys have done work, you know that's one of the most very gruesome time that we have to do. Before we put something onto space, we need to make doubly sure that everything works for the first time and all the time. So we not only get the equipment and put it and shake it as hard as we can, as if you're going to put it on a rocket and the rocket is going to shake it so it doesn't break. We put it into a thermal vacuum chamber and vacuum and put extreme temperatures so that it can survive the temperature of space. And then we also radiate the equipment with radiation as if it would be impacted if it were to, and it will work accordingly. So these kind of things we put us through, called environmental testing. So once environmental testing is done, and I expect probably at the very beginning of the year of next year, we'll come back all the way to Vandenberg over here to circle this wonderful journey of Aquarius and get it launched from Vandenberg. So with that, I just want to let you know that this is how we launch. We have a rocket called a Delta II, which takes off, and it's been very, very successful over the many years. So with that, I was going to show you another launch simulation, a launch, how it looks like. Every launch has been exciting, so I hope you'll find it exciting. It's going to be a similar launch for Aquarius. The movie that you'll see is probably in the early morning, right? But we'll be launching a lot more darker environment.
Launch management net with a readiness to proceed with terminal count. Currently, range, local weather, downrange assets, launch vehicle, and the spacecraft.
And Aquarius is going to be here.
Green.
Launch begins at liftoff with one RS-27 main engine and the ignition of the ground-lit graphite epoxy motors from the western range at Vandenberg Air Force Base. Next, the ground-lit graphite epoxy motors burn out and are jettisoned. After several minutes, the main engine empties the propellant tanks, then cuts off, and the first stage separates from the second stage. Next, the second stage engine ignites and burns, followed closely by the jettison of the fairing. The Delta II is capable of multiple second stage burns and coast periods to deliver each spacecraft into its proper orbit. Separation marks another successful delivery of a NASA spacecraft. For decades, NASA has chosen the Delta II launch vehicle for their space and Earth sciences missions.
So now it gives you an idea of what we're going to go through next year. So moving on to the next part of it is that's where we want to be. There are a constellation of Earth-observing satellites that's going around the Earth taking pictures. And some of you guys who are sitting over here has probably worked on some of them. And it is such a great time to have multiple missions looking at Earth in different ways and trying to figure out and understand the Earth that we live in. So Aquarius over here to be launched in 2011. So now we have one last movie where we want to show you when Aquarius goes into orbit. It's an artist's rendition of how Aquarius would look like as if it was in space. Now I'm going to narrate what you're seeing so that you know which part of the satellites are coming into view. Of course, the Earth limb, as you see, This is Aquarius as if you are moving very close to it. Aquarius is moving around at a very fast rate. What you see, Aquarius is a nadir pointing experiment. It always looks at Earth. And so in order to communicate to Earth, this reflector reflects the radiation into these radiometer channels. These are radiometer and scatterometer areas that look at the radiation from space, from Earth. The antennas, these are star trackers that gives you guidance for the spacecraft to look into the celestial body so that you don't go away from the right direction. And these are the solar panels that generates power to power out the spacecraft. So this is in a way to show you how it will look like if you were standing outside the Earth looking into Aquarius after it's been deployed. So all I have to say at this point is we are going to launch this mission, and it's a more exciting time to come. And studying sea surface salinity from space gives you an understanding, a basic feeling of what to come. This is a sequel, right? I'm sure after the mission is up in orbit, we're going to gather data. We'll come back over here to show you more. And of course, you would have more of a wonderful time. You would probably not have any time to talk to me, but to look at data and understand. So that's the new era that begins. So thank you again, and we will open this forum for questions.
Thank you.
Is there any questions that? Sure.
Can you explain the physics of the detectors, and can you see through clouds? And
Yeah,
the other question is, do you correlate the data that comes from Aquarius with other satellites? You show a picture of all of them, so what can you get by just comparing the data streams from all these satellites?
Yeah, the first question is the L-band. The physics is the L-band radiometer and radar. They all is a microwave. They all penetrate the cloud, except about 10%, 5 to 10% of the time when you have hurricanes and typhoons and a heavy rainstorm. So 90% of the time is cloud penetrating. So it's cloud-free images every week. Second question is the salinity, as I said, is the missing piece of the puzzle. So take many other satellite data and also computer models and the series to put the puzzle together to understand how Earth works. Salinity is one of the many parameters. As I mentioned, 6 different science questions and the different parameters Ahmed showed, and then put them together and understand how climate Earth is working in the water cycle, and improve the better models so we can predict the future.
Any other questions?
Let's see. The Gulf Stream goes very close to the east coast of the United States, and you showed the ocean conveyor belt as being much further offshore, and I'm wondering if the Gulf Stream is part of the, and it moves much faster than this 1,000-year thing you're talking about. So that's a different circulation that's unrelated?
Yeah, the Great Conveyor Belt is oceanography 101. It's the simplest way of showing this conveyor belt. If I show the real geographic location of the Gulf Stream, you'll probably see just a little dots moving, hugging the coast, because the Gulf Stream, you'll talk about 100 kilometers wide and separated from Cape Hatteras in the east coast, and then eventually widens and then moving towards Europe. So Gulf Stream is the fastest moving current. It's moving over 1 meter per second. Over most of the other places, the water moves much slower speed, and particularly at depths. Surface current away from the Gulf Stream, typically 10 centimeter per second, maybe 15 centimeter per second. Over the deep ocean, you'll talk about a few centimeter per second. So in order to complete the whole journey, there's a lot of mixing involved, mixing water from place to place. 1,000-year I've quoted is a statistical averages. If you throw millions tennis shoes, if you plot the picture, and then the middle part, probably on average, you get 1,000 years. Some places you will get much faster, some places much longer.
Okay,
does that answer your question?
The other question I wanted to ask was about the vertical mixing of the salt in the surface layer. I assume that your radiometer is only measuring the top millimeter or so.
Exactly.
You measured the first 1 to 3 centimeters of the top of the water.
Okay. But if you have a rainstorm and there's a little bit of fresh water on the surface, how long does that take to mix, say, in the top 10 feet or the top 100 meters or something like that to get vertical mixing?
Many part of the ocean, the upper mix layer is very uniform. If I show you the temperature salinity profile in tens of meters, and then sometimes even hundreds of meters, if you go to the North and North Atlantic, you go to 1,000 meters, you have the same salinity. So because the wind is stirring the ocean constantly, and there's a lot of mixing going on. So from places, the surface salinity can be used to represent so-called mixed layer salinity. It is represented from a few tens of meters all the way to hundreds of meters.
Most of the remote sensing I'm familiar with is sensing in the gaseous phase and vibrations and rotations of the molecules. So how, can you say a little bit more about the physics of in the liquid state that you're sensing?
The physics is that the radiometer is a passive instrument. They measure the radiation emissivity coming from the sea surface because it reflects from the sun. So the emissivity is a function of temperature, roughness, and the salinity. So the radiometer measures the emissivity, and then we have tens of satellites measure temperature already, and then the scannometer on board measures the roughness, basically how strong wind is blowing. So the number 3 unknowns is the salinity. So basically you measure one thing, you use 2 to derive the other.
So it just is the emissivity variable because of
the dielectric constant is a function of salinity.
Okay, sure.
So basically
conductivity.
We basically measure the emissivity, which is a function of dielectric constant, and is a function of salinity as well. So it's kind of